Class 11th, Subject Physics, 3rd chapter, Motion in a Plane. From the chapter, let us see what is the acceleration. So, the acceleration of any object is defined as the rate of change of velocity with respect to time. The rate of change of velocity with respect to time is called as acceleration of that object, and therefore the acceleration is given by the formula acceleration equal to change in velocity upon time. Change in velocity upon time. Now this acceleration is the vector physical quantity. Its SI unit is meter per second square, and the dimensions of acceleration are 1 in length, 0 in mass, minus 2 in time. Now the acceleration, that is the average acceleration of any object having the velocities v1 and v2 in time intervals t1 and t2 is given by the formula. So if any object is moving with velocities v1 and v2 for the time intervals t1 and t2, then its average acceleration that is average A is equal to change in velocity, that is v2 minus v1 upon time interval t2 minus t1. Let it be equation number 1. So this first equation gives us the average acceleration, that is acceleration of that object for a finite time interval t2 minus t1. So this t2 minus t1 will be sufficiently large here, but instead of that, if this time interval goes to 0, if it is tending to 0, it is approaching close to 0, that means this time interval will be very small. Now at that time we can define the instantaneous acceleration, that is acceleration of the object at that instant of time, is the limiting value of this average acceleration when this time interval tends to 0, when this time interval goes to 0, and therefore the instantaneous acceleration A will be equal to limit t tends to 0, that is time interval will tend to 0, delta v upon delta t, that is equal to dv by dt, equation number 2. So this instantaneous acceleration A is equal to dv by dt. It represents that it is the derivative of velocity with respect to time. Now if we plot the graph of velocity against time, then the instantaneous acceleration of that object at a given interval of time will be the slope of the tangent to that velocity time graph. So the tangent drawn to the velocity time graph will be used to find out the instantaneous acceleration by finding out its slope. So instantaneous acceleration will be equal to slope of the tangent drawn to that velocity time graph. And therefore now let us consider some of the cases in which that object is moving. So let us consider the first case, that object moving with constant velocity. So when that object is moving with constant velocity, at that time the velocity time graph will be as shown, that is the graph will be a horizontal straight line parallel to time axis, and therefore there will be no acceleration of that body as velocity is constant. Change in velocity will be equal to 0, and therefore that body will be moving with 0 acceleration. Now in this case, if this is the graph, this represents suppose v0, that is the velocity which is same at each and every time interval, and therefore if we find out the area of this shaded region, then this area will give us the displacement of the body during the time intervals t1 and t2, because here if you consider area of this shaded region, that area will be equal to its length into breadth. So this length will be equal to phi 0, this breadth will be equal to difference between t1 and t2, and therefore the area will be the product of velocity and time. But velocity is equal to displacement upon time, and if it is multiplied by time, then time will get cancelled and we will get displacement, and therefore this shaded region in this case will represent the displacement of that object between the time intervals t1 and t2. Similarly, now let us consider second case in which that object is moving with velocity phi with positive uniform acceleration. So the acceleration of that body will be positive and uniform, and therefore if you plot the graph, then the nature of the graph is as shown. It is a straight line, but initially suppose that body is having some velocity, and from this we have plotted the graph of velocity against time. Then at that time the velocity is uniformly increasing, and therefore in this case if we find out the acceleration of that object, then that acceleration will be change in velocity, this change in velocity upon change in time. So in this case change in velocity will be phi2 minus phi1, and change in time will be t2 minus t1. Then phi2 minus phi1 will be positive here because this is larger as compared with this, and therefore the acceleration will be positive, that is change in velocity upon change in time will be positive, and therefore that object is moving with velocity phi further, but it will move with positive uniform acceleration. Now in this case if you consider the average acceleration, this will be the average acceleration. It will give us the average acceleration, that is change in velocity upon change in time. It will be similar to that of the instantaneous acceleration if you calculate that acceleration at any instant of time. And again this shaded region will represent the displacement of that object between the time intervals t1 and t2. Similarly, let us consider the third case when the object is moving with velocity phi with negative uniform acceleration. So here the acceleration of that body will be negative and uniform. Again if you plot the graph of velocity against time for this motion, at that time the nature of the graph is again a straight line, but it will not go towards positive side, that is there will be no uniform increase in velocity. The velocity of that body will decrease uniformly. And again if you find out the acceleration, that is average acceleration of the body, then this average acceleration will be now change in velocity upon change in time. But in this case the change in velocity will be phi2 minus phi1 upon t2 minus t1. So that slope of this straight line will be now negative, because as it is phi2 minus phi1, so phi2 is less as compared with phi1, and therefore this difference, that is phi2 minus phi1, will be negative, and hence that object moving with velocity phi will possess negative uniform acceleration. And now let us consider the fourth case in which that object is moving with non-uniform acceleration. That object is moving with non-uniform acceleration. In this case, if we plot the graph of velocity against time, it will not be a straight line, but it will be a curve. So it represents that at different time intervals, the velocity is different in magnitude as well as direction, and therefore we will get curve here. So in this case, if we find out the average acceleration and the instantaneous acceleration, these two accelerations will be different. In the second case and third case, the average acceleration and instantaneous acceleration are the same, but in this fourth case, that acceleration will change point to point, time to time, and that's why we have got this curve. Because if you consider this curve, then the slope of the curve at different points will be different, and therefore in this case average acceleration and instantaneous acceleration will be different. Now we have considered here two time intervals t1 and t2. These are the t1 and t2. If it is sufficiently large, then AB and CD, these two, that is CD is the tangent to this curve at time interval t0 here, will be separated by some finite distance. But instead of that, when this time interval t2 minus t1 is tending to 0, it is tending to 0, at that time this AB line will go towards the tangent CD, towards this tangent CD, and therefore from this the instantaneous acceleration at time t0 will be equal to the slope of this tangent, the slope of this tangent drawn to velocity time curve. Now in this case, again this shaded region will represent the displacement of that object between the time intervals t1 and t2. Now let us find the area of that shaded region under that curve. So it will be found by taking integration, and therefore area under the curve, that is of shaded region, will be equal to integration t1 to t2 integration t1 to t2 phi dt. That will be equal to integration t1 to t2 dx by dt into dt, because this phi is dx by dt, that is rate of change of displacement with respect to time. Dt will get cancelled, and therefore we will get integration t1 to t2 dx. Then integration dx is x, and the limiting values are t1 and t2. Therefore we can put the limiting values and we can write area under that curve will be equal to xt2 minus xt1. So this will represent the displacement of that object, displacement of the object from t1 to t2. So from t1 to t2, what is that displacement that will be given by this, that is displacement at time interval t2 minus displacement at time interval t1, so that we can say that area under the graph of velocity against time is equal to displacement of that object for a given interval of time.